This is the video for the sample test for the solutions for the Chapter 3B test for functions trigonometry. It is our Unit 5 this year. We have to pay attention. We have a no calculator part and calculator part. We're starting out on the no calculator part. On number 1, we're supposed to expand the logarithms below, so we need to use our property of logarithms. I have the log base b of x times y, and I need to know that when I have the product on the inside, that will translate to the sum on the outside. So I have the log base b of x plus the log base b of y when I expand them. The base has to stay the same from the left to the right. That's why I kept it log base b. In the second one here, the log of a quotient is the difference of the logarithms. So this would be the log base b of x minus the log base b of y. I also know that when I take a power to a power, I multiply exponents. So with logarithms, if I have the log of something to an exponent, I can bring that out and write it as a multiple of the logarithm, or multiply by the z out in front. We should be able to know these properties going forwards and backwards. So if I had given you the right side of each of these equations, you should have also been able to condense to the left side of the equation. In the next section, the directions say fill in one number in each of the following blanks. In other words, I'm going to try to simplify whatever I can before I write it inside this blank. So I have 1/2 the natural log of 25. Well, the 1/2 can be brought up, and that would mean that's the square root of 25 in there. I also have plus the ln of 7. Well, the ln of the square root of 25 is just the ln of 5. Then I was adding to that the ln of 7, and I know that two logs that are added is the same as the log of their product. So what's going inside my blank is 5 times 7, or 35. All right, on number 3, I have the log, or two logs subtracted. So two logs subtracted is the log of their quotient. So in the blank, I have 42 divided by 6, which is 7. In number 4, I have the natural log of 16, and I've written that as a coefficient out in front that I need for the natural log of 4. So I need to think of 16 as 4 to a power, and that power was brought out in front. So 16 is 4 to the second power, so I have a 2 out in front of my natural log. On number 5, I have the log of the 4th root of 53. So we need to recognize in this one that the 4th root is the same thing as the 4th power, or the 1/4 power. Then the exponent of 1/4 could be brought out in front, and that's our coefficient now of our logarithm. Number 6 is the change of base formula. If I wanted to put the log base 3 of 17 into a calculator that didn't have a log base function, I would need to do the log of 17 divided by the log of 3, which is the log of the base, or I also could have done that with natural logs instead, which is what was in the problem here. It's the log of what you're taking the log of divided by the log of the base. Number 7 asks me to express as the sum and/or differences of ln of A, ln of B, and ln of C. In other words, to expand this problem as much as possible. So I have the ln of c to the 5th over ab to the 4th. Well, I'm going to start out with my ln of c to the 5th. Since I'm dividing by a, that means I would be subtracting the natural log of a. I'm also dividing by this b to the 4th, so I should also be subtracting the ln of b to the 4th. The last thing I can do is, since I was just supposed to have the ln of a, b, and c, not to an exponent, would be to take my exponents and bring them out in front, realizing that each exponent only goes with its letter. So it's 5 ln of c minus the ln of a, because a didn't have an exponent, minus 4 ln of b. The coefficients can only go with the variable that had each power. Number 8 gives me an expression here. That's a long, complicated expression with logs in it. and it says y is greater than 0, so I don't have to worry about taking the log of a negative number. I'm supposed to express z in terms of y in a form not involving logarithms. That means my final equation down here should be a z equals, and on the right side I might have y's, and I shouldn't have anything with logs. Okay, so let's try to do this. So in order to get rid of the log, I'm hoping that I can put these sort of smushed up, condense them, so that I can have a single log on the right. I have the natural log of y plus 2, and then out here on the end I had minus 2 ln of y's, so I can call that minus the ln of y squared. Now I have the log, or 2 logs, sorry, that are subtracted, which means I can put them together and it would be the log of the quotient of those two things. On the left, I still had my ln of z. Now I have the ln of z is equal to the ln of this fraction over here, which must mean that z is equal to that fraction over there, or z is equal to y plus 2 over y squared. Now z is expressed in terms of y. That means there's y's on the right side of the equation, and there's not involving logarithms. There's no logs left. All right, number 9 is an equation. Remember, on this test with equations, they might be on the calculator or the no calculator part, depending on what's involved in the equation. When I look at this equation, I see it's an exponential equation, and it has 3 terms. There's no way I can put those 3 terms together, so my only option for solving this equation is going to be to solve using factoring. So I have 2. This is an exponential term, which I'm hoping is going to be something squared. Then I have minus 9. This 3x right here, or 3 to the x, sorry, is going to be treated like my variable. And then I have plus 4 is equal to 0. So I know that what is in this spot has got to be my single variable, which in this case is going to be my 3 to the x, because that's the smaller item of the 3 to the x and the 9 to the x. So what I'm hoping is that this first box over here, the 9 to the x, is that same variable squared, and it is, because 3 to the x squared, when you take a power to a power, you multiply exponents, and that would be 3 to the 2x, or 9 to the x. So now I've got this set up like a regular quadratic. If you want to, think of it like 2 times u squared minus 9 times u plus 4 is equal to 0. You could think of it like that when you're factoring, or you could leave the 3 to the x in there. It doesn't matter. So now I'm factoring this, and I'm looking for what 2 things multiply to 8u squared and add to my middle term, which is minus 9u. So if I were going to factor this, I have a 2u squared as my quadratic term, I have a plus 4 as my constant term, and now I'm trying to split up my minus 9u into the remaining 2 boxes. So how can I multiply to positive 8 and add to negative 9? Well, that would be a negative 8u times a negative 1u would multiply to positive 8u squared and add to negative 9u. Then I'm going to take the GCF of my top row here, which is u. Then on the top left, I'm saying what times u gives me 2u squared? Well, that's 2u. What times my u out in front gives me negative 1u? That's negative 1. Down here on the lower left, this number times 2u has got to give me negative 8u, so that must be a negative 4. And then my check, does my negative 4 times my negative 1 equal positive 4? Yes, it does. So to factor this expression, I have 2u minus 1 times u minus 4. Again, if I had written this with my 3 to the x's instead, I would have had 2 times 3 to the x minus 1, and 3 to the x minus 4 equals 0. It doesn't matter which way you do it. Let's scroll down here a little more. My last step is going to be to actually solve, set each of these factors equal to 0. So I'll have 2 times 3 to the x minus 1 equals 0. Or if I add 1 and divide by 2, I have 3 to the x equals a half. To solve this equation, I can either write it in log form, where since the base of my exponential is a 3, the base of my logarithm is going to be a 3. The x used to be in the exponent, so the x is now by itself. And the 1/2 used to be by itself, so the 1/2 is now inside the logarithm. Or I could have taken the log of both sides, and I might have gotten an answer that looked like the ln of 1/2 divided by the ln of 3. And you can see that's the same thing as the answer above, just using the change of base formula. Doesn't really matter to me which way you write it. They're both perfectly acceptable. All right, we still had a second factor over here. We had 3 to the x minus 4 was equal to 0. So we have 3 to the x equals 4. If I convert to log form, my base of my logarithm will be 3, and the 4 is now inside of the log. So I have x equals log base 3 of 4. Or if I had taken the log of both sides, I would have had the natural log of 4 divided by the natural log of 3, which again is the same thing. I can't give a decimal answer on this part because this is the no calculator part of the test, but if it were my calculator part, I could also check this using my calc. Turning over to number 10, we have a log equation. With log equations, it's important to remember that we cannot take the log of a negative number. So when I'm trying to look at my domain for this function, I know that what's inside my log has got to be greater than 0. So I have negative x has to be greater than 0. Well, if I divide by negative to get x by itself, that means x has to be less than 0. I also had my second log expression, which said 3 minus x would have to be greater than 0. Or x, if I move the x over to the right side, x has to be less than 3. So if I'm looking at what's the most exclusive of those two statements, if I have to be less than 0 or less than 3, the most exclusive is that x has to be less than 0. We can do that and restrict our domain in the beginning, or we could just check our answers at the end and plug them in and see if they give us the log of a negative number. All right. In this equation, I had an expression with a log, another expression with a log, and then I have this guy on the end without any logarithms. So when I have logs and things not in logs, I want to put these together so that I have the log of something is equal to a number. So I want to try to condense the left side and leave the right side as just the number parts. So since I have the log plus another log, that's the same as the log of the two insides multiplied together. On the left, I can then distribute my negative x times 3 is negative 3x. Negative x times negative x is positive x squared. Now I need to get rid of the logarithm. The way I get rid of a logarithm when I only have one is to convert to exponential form. The base of this logarithm would be a base 10 because it's a common logarithm and it wasn't written. So 10 is the base of my exponential in exponential form. 1 was by itself, so the 1 is now the exponent of the 10. And then what used to be with the base is now on the other side, all by itself. This is a quadratic expression because it has an x squared in it. To solve a quadratic, I like to have it equal to 0. I'm going to move everything over to the right because I like to keep my x squared positive. I'll write the x squared first and then the minus 3x because that's the standard form for a quadratic. To move the 10 over to the right, I'm going to subtract 10. This is an expression I can factor. What two things multiply to negative 10 and add to negative 3? That would be negative 5 and positive 2. When I set each of those factors equal to 0, I get x equals 5 and x equals negative 2. Remember, in a log, I have to go back and check, could I plug each of these into the original problem? I know my domain was that I can only have negatives. So this x equals 5 is going to be crossed out. You could tell if you plugged back into the original problem right here, if you plug in a 5, you're taking the log of negative 5, which does not work. So in this case, the negative actually does work. When I go to plug negative 2 into the original problem, I would be taking the log of the opposite of negative 2, so the log of positive 2. In the second log, I would be taking the log of 3 minus negative 2, or the log of positive 5, which also works. So I can see that x equals negative 2 is the only answer that works. The other one was extraneous. Number 11 is another exponential equation. I have an exponential on the left and an exponential on the right. Ideally, I'll be able to get these two to have the same base and I won't need to use logarithms. In this case, I see 125. 125 is 5 to the third power. So I'm going to replace my 125 with my 5 to the third power because on the left I had 5 to the 8 minus x, and now I'll have like bases. Remember, the right was also raised to the 2 minus x power. So I need to keep that as well. So now I have 5 to the 8 minus x on the left, and on the right, when I take a power to a power, I multiply exponents, and this is really 5 to the 6 minus 3x. If I have my bases the same, they're both 5s, then that means my exponents must also be equal. So I have 8 minus x is equal to 6 minus 3x. This is a standard linear equation. There's no exponents or anything in there. So I just want to get my x's on one side and the numbers on the other. I'm going to move my 3x over to the right by adding it, because I like my x's to be positive, and negative x plus 3x is positive 2x. I'm also going to move my positive 8 over to the right by subtracting it, and 6 minus 8 is negative 2. Last step would be to get the x all the way by itself, so I will divide both sides by 2, and I'll have x equals negative 1. It's an exponential, so I don't have to plug my answer back in and check, but if I did, x equals negative 1 will work. All right, number 12 on the no calculator part. I look at this, it's an equation, it's a log equation, and I have a number that's not in the log and stuff that's in a log. When I had that happen, just like over here in number 10, I'm going to try to condense into the form where I have the log of something equals a number. So I am going to move that 6 over to the right side and get it by itself. I also know that I can't take the log of a negative number. In this case, what I have inside my logarithm is x minus 16, the quantity squared. Since it's a quantity that's squared, that means that it's always going to be positive. So any answer I get for this problem should be one that'll work. All right, so now I've got the log of something equals a number. My method is to convert to exponential form. This is a natural log, so the base is e. So when I convert, the base of my exponential will be e. The 6 used to be over here on the right by itself will now be e's exponent. And then what used to be inside the logarithm, which was x minus 16 squared, is going to be over there by itself. Now this is a place where you guys have a tendency to make a mistake. We see that we want to get rid of the squared on the right to solve this problem. Don't forget to get rid of the squared. When you square root both sides, you always need to plus or minus because what's inside could have been positive or negative. Then I need to get the 16 away from the x. So I'm going to add 16. It doesn't matter if I write 16 plus or minus the square root of e to the 6th, or I could write plus or minus the square root of e to the 6th plus 16. Either one is fine. The other thing that hopefully we realize is that this expression could be simplified. This is really e to the 6th to the 1/2 power, because the square root is the 1/2 power. So I could also write this as 16 plus or minus e to the 3rd is equal to x. And one of those will be positive and one of them will be negative, but that's not going to matter when I go to plug them in because I would square them. Now I'm scrolling over to part 2 of the test, which is the graphing calculator allowed part. Let's be sure we read the directions. Even though our calculator is allowed, we still have to show all work, and it says to store intermediate answers in your calculator to ensure accurate results. That means if you're typing things into your calculator at the beginning of the problem, be sure you're using the answer button rather than just chopping off numbers and reusing the decimals. Also, we need to truncate to 4 decimal places when we write our answer on our paper. That means we're going to chop 4 places after the decimal. All right. Number 13 says to solve each of the following equations algebraically for x. Give both an exact and a decimal answer. When I look at number 3, I have an exponential on the left and an exponential on the right. But the bases are 2 and 5. They have nothing in common, so in order to solve this, I'm going to take the log of both sides of the equation. It doesn't matter if I take an log log or a natural log, so long as I do the same thing on both sides. I usually do ln because that's what we use more in calculus. The reason that I did this is because now I can take my exponents and bring them out in front as a multiple of the logarithm. So now I have 5 minus x times the ln of 2 equals 2x plus 3 times the ln of 5. Remember that we needed to put those exponents in parentheses because both of the things in the exponent went with the ln of 2. So if I distribute my ln of 2, I really have 5 ln of 2 minus x ln of 2 equals, and I distribute on the right, 2x ln of 5 plus 3 ln of 5. Although this looks like an ugly equation right now, I realize I have 5 ln of 2. That's just a number. I have minus x ln of 2. Well, this is x times a number. Over here on the right side, I have 2 ln of 5 times x, which again is just a number with the x, and I have 3 ln of 5, which is just a number. So this is really just a linear equation with ugly coefficients. In order to solve an equation like this, I like to get my numbers with x on one side and my things without x on the other. So I'm going to move my x's over to the right in this case because this was a minus. Usually I move them on the left, but I like to keep things positive. So on the right, I would have had my 2x ln of 5 that was already there, and then I'm going to add my x ln of 2 when I go to move that over. Then I have the things that were on the left. Already on the left, I had my 5 ln of 2, and in order to move the 3 ln of 5 over to the left, I'll do that by subtracting 3 ln of 5. All right. So now, on the left, I just have this crazy number, this 5 ln of 2 minus 3 ln of 5. On the right, I have two things that both have an x in them. In order to combine them, I'm going to factor out x as the GCF. If I took the x's out of those, I would have 2 ln of 5 plus the ln of 2. Remember, all that in blue there, that's just a number when I put it together. On the left, I haven't done anything. I still have 5 ln of 2 minus 3 ln of 5. My last step is going to be to get this x by itself. And to get this x by itself, I've got to take this whole big factor in blue and divide it over to the other side. So I just covered up that other problem for a second. On the left, I had my 5 ln of 2 minus 3 ln of 5. And then I divided this 2 ln of 5 plus the ln of 2 over to the other side. So I'm not going to worry about the fact that this is not pretty. This is my answer. You might have gotten the answer written in a different form. If you had moved the x to the other side of the equation, you likely would have had 3 ln of 5 minus 5 ln of 2, or both of these would have been negative. Sorry, your 3 ln of 5 would have been negative and your 5 ln of 2 would have been positive. And then what would have both been negative were your two denominator terms. You would have had minus 2 ln of 5 and minus the ln of 2 in the bottom. It doesn't matter. This is the same thing. The way I can easily check my answer is by typing these guys into the calculator. The directions also said I was supposed to get an answer accurate to 4 places after the decimal. Just watch your parentheses when you're typing things in. I have 5 ln of 2 minus 3 ln of 5. Now, if you're using your TI calculator and it opens the parenthesis for each of your logs, be sure you close those parentheses. So you'd have a lot of double parentheses going on. And I divided by 2 ln of 5 plus the ln of 2. And I can see that my decimal answer is negative 0.3483. So I was supposed to give that, there, get my calculator back up there, as both an exact answer and a decimal, which I've done both of those. No matter what form you got your answer in, you also should have had the same decimal. Okay, so moving on to number 14 here. In this one, I have something with an exponential and something that's not with an exponential. So I can either convert this to log form or I can take the log of both sides. It's not going to matter. If I took the natural log of both sides, I would have the natural log of 3 to the negative 3x equals the natural log of 0.001. Then I would bring my exponent out in front, and I'd have negative 3x ln of 3 equals the ln of 0.001. To get this x by itself, I need to divide by the numbers that are with it. So on the right, I had my natural log, and I'm going to divide by the negative 3 and the ln of 3. I need to divide by all of those. So this is a fine answer. we also need to give a decimal equivalent. So if I type this into my calculator, making sure I put the whole bottom here in parentheses, I'll get my calculator back, I have 2.0959. So that would be my decimal version of this answer. I will go through and do this problem also the other way. If you had, instead of taking the log of both sides, just converted to log form, I'll try and smush it in here, then the base of your exponential was 3, so the base of your logarithm would have been 3. What used to be by itself is now inside your logarithm, and then what used to be in the exponent is now over on the right side by itself. Then I would have just divided both sides by -3, and I would have had -1/3 the log base 3 of 0.001. That's really the exact same answer that I had written in a different form using the change of base formula. If I typed this into my calculator, I would have gotten the same decimal, so I know that that's okay. All right, now we have some word problems. In number 15, we have the number of fruit flies in an experimental population grows exponentially. At time 0, there are 20 fruit flies. After 5 days, there are 30% more fruit flies. How long will it take to have 200 fruit flies? So there's more than one way to do this problem, but the way I would see it is using our formula, the amount you have at the end is the amount you have at the beginning times the rate, and then you look at how many times does this process repeat, and that's your exponent. So let's look at what we have here. At time 0, there are 20 fruit flies. So that means my a sub 0 is 20. I want to know how long will it take to have 200 fruit flies. That means my amount at the end is going to be equal to 200. And those are the two amounts of fruit flies that I have. I also need to know what the rate is in this problem. Now, it's not really stated explicitly, but after 5 days, there are 30% more fruit flies. So my rate's not 30%. 30% would be making me get smaller. After 5 days, I have 130% of what I used to have because I keep the flies I have and then I get 30% more. So my rate in this case would be 1.3. I'm kind of looking at how long it's going to take, so what I'm looking for up here is my number of repeats. In order to solve this equation, I would divide both sides by 20 to get rid of the coefficient. So now I would have 10 equals 1.3 to the n, where n is the number of repeats. In order to solve this equation, I could take the log of both sides. I'll bring out the exponent at the same time. And then to get n by itself, I'm going to divide both sides by that ln of 1.3. And I have n is the ln of 10 times divided by the ln of 1.3. So this is how many repeats. The thing that I haven't taken into account is it repeats every 5 days. So this is how many repeats. So I'm going to need to take this and I'm going to need to multiply it by 5. So I'm going to have 5 times the ln of 10 over the ln of 1.3 days. Now that's not really a very nice number, so let's put it into our calculator and see what we get. I have 5 times the ln of 10 divided by the ln of 1.3. And this is telling me it would take 43.8814 days. 43.8814 days. I always think it's a good idea in a word problem to go back and be sure it makes sense. So let's say we started out at time 0, we had 20 fruit flies. So I'm going to hit enter. Then I'm going to multiply by 1.3 so that I now have, after 5 days, I'd have 26 fruit flies, which is an increase of 30%. So that was 5 days. I'm trying to get up to 200. So if I hit enter again, now I'm at 10 days. Then I'm at 15 days. Then I'm at 20 days, 25 days, 30 days, 35 days, 40 days, and you can see one more, 45 days. At 45 days, I've exceeded 200, so it should make sense that at 43.3, that's when I hit exactly 300. You can't just do this by a strict proportion. You have to use the exponential to do it. but your answer checks out, so that looks good. All right. Let's go up here to number 16. Number 16, using carbon dating to measure radioactive decay, scientists can determine a fossil's age by how much carbon-14 is present. The half-life of carbon-14 is 5,730 years. If a recently deceased animal contains 5 grams of carbon-14, about how old is a fossil with 0.575 grams of carbon-14? So this is not a money problem. It's going to follow our standard rule where the amount at the end is the amount at the beginning times the rate to the number of repeats. And let's look at what we have. It says we start out with how many grams? A new deceased, animal is going to have 5 grams, so that's the amount at the beginning. We are looking to end with 0.575 grams. I know my rate because this is the half-life, so my rate must be a half. But the weird thing for this one is in the number of repeats. This process isn't going to repeat every year. It's going to repeat every 5,730 years. So I could put in here y divided by 5,730, or I could just solve for the number of repeats and then adjust accordingly. I usually put it in this way. All right, so I need to get the exponential by itself. So the first thing I'm going to need to do is I'm going to need to divide the 5 to move that over. So I'd have 0.057 divided by 5. I'm not going to do that yet in my calculator. I'm just going to leave it that way, and I'll wait and type some stuff into my calculator at the end. All right, now in order to get rid of the y and the exponent, I'm going to take the log of both sides. So I'm just going to sneak a natural log in there. And the reason I did that is because now on the right side, I'll be able to bring that exponent down in front. So I have y over 5,730 times the ln of a half. So in order to get the y by itself, I'm going to need to multiply the 5,730 over to the other side. The other side already had this natural log expression. And I also am going to have to divide the ln of a half over to the other side. You can write it as all one big ugly fraction. That's fine. This is how many years. That's a crazy expression, so I'd like to also get the decimal equivalent. So I put that into my calculator, and I have 17,879.2859, and that was in years because when I expressed the half-life up here in the problem, it was in years. So you just need to keep the same unit as the half-life in. That's going to be the unit for the final answer. Does this seem like a realistic answer? Well, let's jump back to our calculator. We started out with 5 grams. I'm going to take half of that. So after 5,000 years, I have this much. It's closer to 6,000 years. Okay, 6,000 years. Do it again, that's about 12,000 years. Do it again is about 18,000 years, and that's almost the number I was looking for, so my answer of close to 18,000 years looks like the right ballpark. We know that carbon dating for fossils takes a long time, so it's a realistic even though it's a large amount of years. All right, number 17 is an interest problem. It says, suppose that $1,200 is invested at an interest rate of 9.6%. That's always an annual percentage rate, we know. How long will it take for the investment to double in value if A, the interest is compounded quarterly, or B, the interest is compounded continuously? So we need our interest formulas. For regular interest, like compounding quarterly or daily or monthly or any of those guys, I have my formula, and we'll give you those formulas on the test. For continuously, we know that's the formula with the E in it, and we need to know which formula applies to which part of the problem. So let's look at what we know. The principal is the same for both problems. The principal is $1,200. I'm trying to double my money. If I'm trying to double my value, how much do I have over here on the left at the end? I would have $2,400. Now, it wouldn't matter if they gave me an initial amount or not. Whatever number I have as the principal, I would have to double it over there on the left side. All right, then I have my rest of my formula. I've got 1 plus R. R is the interest rate, but that has to be as a decimal. As a decimal, this number is 0.096. I have to move the decimal 2 places. N is the number of compounds per year. This problem was quarterly, which means 4 times per year. In the exponent, we have another n, which would be 4, and then we're looking for how long will it take, so we're looking for the t. Okay, I just gave myself a little more room there. All right, so the first thing I'm going to do is I'm going to want to move this 1200 over to the other side to try to get the exponential by itself. So I have 2400 divided by 1200, which is 2. That should make sense because I'm doubling. My amount at the end has to be double what I started with. Okay, so now in order to get this out of exponential form, I'm going to take the log of both sides. So I'm just going to sneak in a natural log on each of mine so that in the next step I can take my exponent and I can pull it down in front. So now I've got the ln of 2 is equal to 4t times the ln. Now I know that you could add these expressions together. I prefer to wait to add them until I've got it all into my calculator. So now I've got all this stuff over here on the right is times t. But again, it's just a number, so how am I going to move it to the other side? I'm going to divide by the 4 and the ln stuff. So t is going to be the ln of 2, and then all of that was divided by 4 ln of this big expression I had going on for the inside of my interest formula. Okay, that's a number that I can't think of right now, so I'm going to have to use my calculator to try and evaluate what this is. So I typed that into my calculator. I got 7.3065, and the answer to that would be in years because the answers to these questions in money are always dealt with in years because we started with an annual percentage rate. So even though it's compounded quarterly, my answer T is always the time in years. That was what went into the formula. All right, let's go ahead and scroll down and do B. So just like before, my amount at the end would be the $2,400. My principal, or the amount I started with, is the $1,200. I have no idea where my pen turned red in the middle there. And that was E. E is E. That's the letter E. We got to leave it there. It's a constant. My R was 0.096, and I don't know what T is. That's what I'm looking for. So just like before, I'm going to start out, and I'm going to divide by the 1,200 to get my exponential term by itself. Then I'm going to either convert to natural log form or take the natural log of both sides. So if I just throw a natural log in front of each of these, I should realize then that I can bring my exponent here down in front. And in this case, I have the ln of e, which is going to be gone because that's just times 1. So now my coefficient of t is this interest rate, which I will divide to move over. I'll give myself a little more space. So I have t is the ln of 2 divided by the 0.096. I don't know what that is, so I'm going to go to my calculator. And in this one, I got 7.2202 years. Notice I didn't give any estimate of checking both of these, but I realized that since I did 2 different interest formulas, just changing the amount of time, which frequency with which they were compounded, I should get answers that are pretty close, and I did. So those look like pretty good answers to me. Okay, I think we have a little more on the back here. In number 18, I have the mass, m grams, of a radioactive substance is given by the formula m equals 160 e to the negative 0.02 t, where t is the time in weeks after the mass was first recorded. Showing all work, giving answers correct to 4 decimal places, state the value of m, which was the mass, when t was equal to 0. So all this is really asking us to do is to take our original problem right here and plug in t equal to 0. So I should recognize, even without my calculator, that anything to the 0 power is equal to 1. So I have 160 times 1. So m would be 160. I told you in the problem it was grams. So m is 160 grams. Even if you didn't plug in 0, you also probably should have noticed that this is following that same pattern where we have the amount at the end is the amount at the beginning, and then the rate and the repeats going on. So my initial amount would be 160. So that seems to make sense. Question B says find the value of t when the mass has decayed to half of its initial size. Well, half of its initial size would be 80, so I can plug in 80 for m. and the right side of my equation is just staying the same as it was in the original problem. Now I need to get the exponential by itself. So I'm trying to get this by itself. I need to divide the 160. When I move it over, I would have 1/2 on the left, and that should make sense because I was trying to get to half of what I started with. Now I can either take the ln of both sides or convert to natural log form, however you want to think of it. I've got the ln of 1/2 on the left. I can bring my exponent down in front, and I have negative 0.02t. The ln of e was just 1, so I don't need to write that down again. I'm going to divide by my coefficient of t to move it to the other side, and I have t is the ln of 1/2 divided by the negative 0.02 number. I don't know exactly what that is, so I'm going to go to a calculator. Okay, so I typed this one into my calculator, and I have 34.6573 weeks. And that seems like it would be a realistic amount. If I started out with 160, I know that I'm decaying because my exponent was negative. And I can also see that if I plugged this back in, I just redid my calculator with plugging in the answer that I got for t in the problem, and I can see that I had 80.0009. So that looks like it should be a good amount. I'm at about half. Looks like we have one more problem down here on the end, so I'm going to scroll down. Number 19. The number of girls who participate in Girl Scouts decrease as the girls get older. In a rural community, a class of girls is followed from first grade through high school. The number of girls participating each year is modeled by this function, p equals 200 minus 70 log of t plus 1, where t is between 1 and 12. P is the number of girls participating, and T is the time in years. How long will it take for the total number of girls to fall to 150? So I'm looking for the total number of girls, which would be the P, to equal 150. So I'm just plugging that into my equation. Now this is an equation with a log in it, so it has logs and things not in logs. When that happens, I like to get the log by itself. So first I would subtract to move the 200 to the other side, and I'd have negative 50 is negative 70 log of t plus 1. Then I would divide both sides by the negative 70 to get that by itself. I'm just going to simplify negative 50 divided by negative 70 to positive 5/7. You could leave it as negative 50 over negative 70 if you wanted to. Now I've got the log by itself, so I'm ready to convert to exponential form. This is a regular old log, so that means the base of my log is 10. So the base of my exponential is 10. The 5/7 used to be the answer to the log, so it's now the exponent in the exponential. And what used to be inside the log, the t plus 1, would now be separated by itself. I also, to get t by itself, need to subtract 1. So I have t is my 10 to the 5/7, subtract 1. Okay, so I'm not sure exactly what that is, so let's go ahead and turn it over into a decimal. So I went ahead and typed that into my calculator. Be sure that you put that decimal there, that exponent in parentheses, or it's not going to put the divide by 7 in there. Then with my answer, I had 4.1794, and to get units for that, it told me up here in the problem, t is the time in years. So I just put years on there as my time.